In the last lecture, we started the discussion of hydrogen atom problem. Okay, and I showed you how to set up the Hamiltonian. Okay, and how to carry out the solving the Schrodinger equation. Okay, I didn't do the complete derivation, but I showed you how to do that. Now, after solving the Schrodinger equation, we get the expression for energy, which depends on the quantum number n, called principal quantum number. Okay. So, what's the expression for energy? En equal to minus 2 pi square mu z e square divided by m z square e power 4, right? Yeah. Mu z square e power 4 by 4 pi epsilon naught the whole square into n square h square. This is the expression for energy, where mu is called the reduced mass, but I have told you reduced mass, right? It is approximately equal to mass of the electron itself. Okay, because if you compare mass of a proton and the mass of electron, mass of proton is nearly 1837 times heavier than mass of an electron. So you can neglect mass of electron in the denominator quantity of reduced mass, and if you do some arithmetic, we get reduced mass is approximately equal to mass of electron. Okay, almost equal to mass of electron. So even if you put mass of electron in the place of reduced mass, nothing wrong in it. Now, and last class I showed you that if you substitute the proper constants, okay, we get minus 13.6 into z square by n square, and we get the energy in electron volt per atom. This will give you energy in electron volt for one atom. Okay, if you want energy in joules or kilojoule, you can use this formula, En equal to minus 1312 z square by n square kilojoule per mole. You can use this formula to calculate energy of the electron in the nth state, where n is the principal quantum number. Okay, about energy we discussed in the last class, but I will give some more information, then I will continue. Okay, so yeah, so this is what we discussed in the last class. Energy of the ground state, if you put n is equal to 1, what are the allowed values of n? I have told you. Allowed values of n are 1, 2, 3, 4, 5, etc. In the case of hydrogen atom, n is called principal quantum number, and it can take values 1, 2, 3, 4, etc. If I put n equal to 1, we will get the ground electronic state. Okay, so what is the energy of the ground electronic state? Put n equal to 1, and for hydrogen atom z equal to 1, so you will get minus 13.6 as the ground state. And for ground state, n value is 1. N value 1 means the possible L value should be 0. If L is 0, then the possible ML value is also 0. Therefore, this 1, 0, 0 represent a state. Okay, isn't this 1, 0, 0 represent a state? We write each state as a wave function, right? So the wave function for this state is given as 1, 0, 0. Psi 1, 0, 0. Then, if I put n is equal to 2, we get the energy as minus 3.4 electron volt. And if you put n equal to 2, there are two possible values of L. If you put n equal to 2, there are two possible values of L, L0 and L1. If L value is 0, the possible ML value is 0. Therefore, we have one state which has the quantum numbers 2, 0, 0. So 2, 0, 0 will give one state. Then 2, if L is 1, there are three possible values of ML, plus 1, 0 and minus 1. So 2, 1 plus 1, 2, 1, 0, 2, 1 minus 1 will give you three states. So 2, 1 plus 1, 2, 1, 0, 2, 1 minus 1. So altogether, this level has 4 states, degenerate states. Okay, so degeneracy of this level is 4. Okay, right. So like that, we can have many electronic levels. Okay, I'll give you at least the next electronic level so that we can make some comparisons here. So minus 13.6. If you put n is equal to 3, so 3 square is 9. So 13.6 by 9 will give you the value as 1.511. 1.51 electron volt. This is the energy of n is equal to 3 level. N equal to 1 level is ground level. Ground level has only one state. N equal to 2, okay, is the next higher level, which has 4 state. N equal to 3 is the next higher level, that is second excited level, I can say, which has n value 3. Therefore, there are 9 states possible. Here we have 4 states. Here 9 states are possible. 1, 2, 3, 4, 5, 6, 7, 8, 9 states. So degeneracy is 9. Now, what about the gap between these two levels? Listen, if you want to find the gap, you subtract the lower value from the higher value. So what is the gap between E2 and E1? E2 and E1. So the E2 is 3.4 minus 3.4, and this becomes minus or minus plus. So 13.6 minus 3.4 will give 10.2 electron volt. Listen, the gap between the ground level and the first excited energy level is 10.2 electron volt. What about the gap between the next two levels? That is E2 and E3. So what to do? Subtract this 1.51 from 3.4. So 3.4 1.51 will give 1.89, correct, no?
Yes, sir.
Yeah, it is, the gap is 1.89 electron volt. Observe carefully. This gap is very large. While drawing, I didn't draw in a proper manner. Actually, this gap should be large and this gap should be small. Because this is 10.2 electron volt, whereas this is just 1.89. So, keep this in mind. In the case of a hydrogen atom, exciting an electron from ground level to first level require higher energy than exciting an electron from E2 to E3. As we go above and above and above, what happens? The gap decreases. Okay, right? Listen, below this zero, the energy levels have negative value of energy, which indicates that these states are bound states. These are all called bound states. Let me write here. These are all called bound states. Bound states. Whereas the electrons which are having energy above zero, they are called free state or scattering states of the electron. Okay, scattering states. Right? Yeah. So bound states have negative value of energy. Keep that in mind. Okay. So wave function of hydrogen atom, right? The hydrogen atom wave function depends on 3 quantum numbers n, L and ml. It depends on 3 quantum number n, L, ml. Okay, we call this type of wave function as spatial wave function. Spatial function. Spatial part of the function. We can say like spatial part. Okay. If I include spin, then it is called spin part or a spin orbital. Okay. One second. Hydrogen atom wave function depends on 3 quantum numbers n, L, ml. We call this wave function as spatial part of the wave function. Okay, spatial part function. Listen, if I include spin, then it is called the full wave function. Okay, so now without spin, it is called spatial part of the wave function. Okay, we'll discuss spatial part, then we'll discuss about spin part later. Okay, now listen. So, depending upon the quantum number, we have different orbitals. Okay, you might have heard about that. Okay, listen. If I put, say, n is equal to 1, that's the least possible value of n. N equal to 1. N equal to 1 means the only possible value of L is 0. If L is 0, the only possible value of ML is 0. Okay, ML value is 0. Right? Now, this corresponds to, if L is 0, we call that subshell as S subshell, and ML is 0, so you will get a particular orbital. Okay, so it is called S orbital. So this wave function, psi, n value 1, L value 0, ML value 0, psi 1, 0, 0 is actually called as psi 1s of hydrogen atom. N value is 1, N value is 1, L0 means it is S subshell, and we are giving particular value of ML, so it should be an orbital. Okay, listen, for a given N, for a given L, for a particular value of ML, we will get an orbital. So this is the wave function for 1s orbital. Okay, right, listen, so what is the wave function for 1s orbital? How to write that? Listen, it's actually easy. See, wave function of hydrogen atom, the general wave function, let me write here. General wave function, right? Which we write simply as psi n L ML, right? We can separate this into two parts. One is radial function, okay, which depends on radius. It also, it depends, it varies with R, it depends on two quantum numbers n and l. Radial function depends on two quantum number n and l. And we have an angular function which depends on the variable theta and phi, and depends on two quantum number n, l and ml. I repeat, the total, that is spatial wave part of the wave function, it can be separated into two. One is called radial part, a radial function, radial part. The other one is called angular part of the wave function. Remember, I did not include spin here. Without spin, it is called spatial part of the wave function. Okay, the spatial part is separated into two. One is called radial, the other one is called angular part. Listen, I am going to give you the general expression for radial part. Right? Radial part, which depends on two quantum number, can be given as. Observe carefully. We have to include some constant, normalization constant, let me call it as n. Okay, some normalization constant should be there into r power L. R is the radius, distance between the nucleus and the electron, and L is the azimuthal quantum number, because the radial part of the wave function depends on n as well as L. Into, we get a polynomial. We should get a polynomial of degree n minus L minus 1. There should be a polynomial of degree n minus L minus 1. I'll tell you what is these things about. Then we'll be having an exponential part, e power minus zr by n into a0, where a0 is nothing but Bohr radius in the case of hydrogen atom. Okay, this is the radial part of the wave function, note down. This is a general way of writing radial part of the wave function. Okay. So, what I am going to do now, first let me focus on radial part. Okay, once we get some idea about radial part, then we'll discuss about the angular part. Okay, so we'll discuss about the radial part. Right, listen. First, the first wave function is 1s orbital. So, I'll take 1s orbital. 1s orbital means n value 1, L value 0. Okay, for radial part, ML value is not necessary, but if you want, you can write, nothing wrong with it. For radial part, we need only these two. Okay, now if we write the radial part of the wave function R, radial part for 1s orbital, n value is 1, L value 0 means yes. Okay, a radial part of the wave function, it depends on the variable R, is equal to normalization constant n. Observe carefully how I am writing. Okay. This is the procedure you should follow. Then R power L value. L value is 0. L value is 0. Then what is n minus L minus 1? N minus L minus 1. See, n value is 1. L value minus L value is 0. Then minus 1. As per this formula. 1 minus 1 is 0. So L minus L minus 1 0 means the polynomial of degree 0. Which means there should be only one constant a. The polynomial should contain only one constant because the degree value is 0. Then e power, since we are writing oneness orbital wave function for hydrogen atoms, our focus is on hydrogen atoms. In the case of hydrogen atom, z value is 1. So e power minus z into r. Z is 1, therefore r by n value is 1, so 1 into a naught. R power 0, anything power 0 is 1. This is just a constant, right? Constant into n will give another constant. Let me write that as normalization constant n. Just normalization constant. Don't worry about this n and don't compare. Or if you want, you can put n0 here. n0 into a will give you another constant n. Into e power minus r by a naught. This is the radial part for oneness orbital. Okay, take note. If you plot this radial part of the wave function, r oneness in y-axis and r, small r in x-axis. If you plot, if I put r equal to 0 here, if I put r equal to 0, I get e power 0. E power 0 is 1. 1 into n is, you will get some value. Yes, you will get some value at r equal to 0. Then, as r increases, as small r increases, what happens? I have minus sign here. As small r increases, we have minus sign, therefore it decreases exponentially. The function decreases exponentially. Okay? This is how the wave function look like. A radial part of the wave function look like for oneness orbital. This is for oneness orbital. Okay, and what is the probability? Radial probability. Radial probability, take the square of this. R, oneness, R. You take the square of this part and plot this versus R. If you take square, I'll get n square. If you take square, I'll get n square. And here I'll get e power minus 2r. E power minus 2r by a naught. Okay. So, if you plot again, the probability also look like this. It is also exponential decreasing function. Right. So, what does this indicate? Probability is maximum at r equal to 0. See, probability value is maximum. As r increases, probability decreases. Probability is maximum at r equal to 0. R equal to 0 means center of the nucleus. So, which indicate that the electron is present inside the nucleus, which is wrong. Therefore, listen, because wrong means, listen, we plotted probability in a wrong manner. What is actually radial probability? Listen, you have to plot this r square multiplied by 4 pi r square. 4 pi r square. Okay, you take the surface area of the sphere. Okay, multiply this quantity with the radial part. R oneness r square. This is called radial probability distribution. If you plot this quantity versus r, now what will happen? At r equal to 0, if you put r 0 here, the entire quantity becomes 0. Then as r increases, what will happen? Initially it increases almost in a parabolic manner, then it decreases in an exponential manner. This is called radial probability distribution, and listen, see, there is a maximum, and this distance is what we call as RMP, most probable distance, RMP, no doubt. Most probable distance for oneness. Okay, how to find most probable distance? We'll do that. Okay, just take note of this. Listen. So, the radial probability distribution plot for oneness orbital has one peak. I will get one peak here. One peak. For oneness orbital, we will get one peak. If we go to 2s orbital, but before going to 2s orbital, I will show you how to find this RMP. Okay, most probable distance, meaning from the nucleus. Okay, probability of finding electron increases. At one particular distance, probability of finding electron is maximum. After that, the probability again decreases. Now the question is, at what location probability of finding electron is maximum? How to find out? That is the RMP. Most probable distance. Most probable distance at which the probability of finding electron is maximum from the nucleus. Okay, how to do that? How to find out? Yeah, listen. So I have shown you the radial part of the wave function already, right? So what is the radial part of the wave function for oneness? For oneness orbital, the wave function is, it consists of a normalization constant, then e power minus r by a naught term. Am I right? Is this correct? Check it. To find the most probable distance RMP, what to do? We have to differentiate this quantity. What's the quantity? 4 pi r square into the radial part of the wave function square. Differentiate this with respect to r. This is, we plotted in y-axis, r we plotted in x-axis. So dy by dx. Okay, and put that value equal to 0. You will get the maxima or minimum. Okay, it's very simple. Now listen. So differential of d by dr, that we write d by dr separately. So we have 4 pi r square into r square. Listen, this is r. Take the square. N square into e power. If you take square of this, you will get e power minus 2r by a naught equal to 0. Now what to do? We have to differentiate. But before that, 4 pi n square, these are all constant. You can keep it out. 4 pi n square, you can keep it out. So what we left with is d by dr into, I have an r square term here and an exponential term here, e power minus 2r by a naught equal to 0. Now observe carefully. If you bring this quantity to the right hand side, it becomes 0. So you need not worry about the constants. Okay, it becomes 0. Now you have to differentiate this. Apply UV method. First you keep u as such. I'm differentiating. Okay, keep u as such. Differentiate this. You get e power minus 2r by a naught. Exponential and differentiation will give same thing. Then differentiate the power term. What's the power term we have? 2r by a naught. R and differentiation will give 1. So you'll get minus 2 by a naught. Okay, next plus keep v as such. What is v? E power minus 2r by a naught. Keep this one as such and differentiate r square. R square on differentiation will give 2r equal to 0. Take two. Listen, if you take e power minus 2r by a naught as common and if you bring it to the right hand side, it becomes 0. So I can write directly as r square into minus 2 by a naught, okay, plus 2r equal to 0. Now see, this is minus 2r square by a naught. No, bring it to the right hand side. So I'll write in the next page. So 2r equal to, I'm keeping 2r as such. I'll bring this term to the right hand side. So it becomes plus, right? Plus 2r square by a naught. Correct? Plus 2r square by a naught I get. Okay. Now, so 2 cancel each other. R square you can cancel. So what is r? Here I have 1.
A naught.
R is equal to a naught. What is this r? This r is nothing but RMP. So what do you infer from this? So if you simplify this, you will get RMP equal to a naught. What does it indicate? It indicates that the probability of finding electron is maximum, okay, at a naught for oneness orbital of hydrogen atom. Okay. Let me take the next wave function number 2, that is 2s orbital. For 2s orbital, n value is 2. Since it is s, L should be 0. If L is 0, the only possible value of ml is 0. Okay, but for radial part, we need only these two. Ml is not necessary. Now, what is the radial part of the wave function for 2s? It consists of a normalization constant. Let me write initially L0. Then R power L0. Then we will get a polynomial. What is the polynomial? See, n minus L minus 1 you should find out. What is n? N is 2 now. Minus L value is 0. Minus 1 because for s orbital L value is 0. Okay, and we have minus 1 here. So 2 minus 1, I am getting 1. Now the polynomial should have the degree 1. What does it mean? It means that the polynomial should have a radial r power 1 term and a constant. Okay, into e power minus z value for hydrogen atom, z value is 1 into R by n value is 2 now, so 2 into A. This is the radial part of the wave function for 2s orbital. Take note. Then for this wave function, if you plot, now I am going to give you the radial probability distribution directly, which is 4 pi r square into radial wave function of 2s orbital square. Okay, and plot this versus r. If you plot this versus r, listen, you will get a small maximum and it becomes 0, and then it increases again and goes to a maximum, then it decreases like this exponentially. It has two peaks. It has two peaks. Yes, for 2s orbital we get two peaks. For 1s orbital 1 peak, 2s orbital 2 peak, 3s orbital we get 3 peaks. Like that it goes in the radial part. Now the probability is maximum here. Okay, and this is the RMP. This is the RMP for 2s orbital of hydrogen atom. Okay, this is not RMP. This is actually you will get a small probability near to the 1s orbital location, but the maximum probability is here. Okay, but we have a node that is interesting point. See, we have a radial node. Okay, I am plotting radial function and the probability becomes 0 at one particular point, and that is called the radial node. Okay, it has a radial node, right? Take it. 2s orbital has one radial node. Now, we have a general formula to find radial node and all. We will discuss that as we go along. This is for 2s orbital. Likewise, we can write the wave function for any orbital. That is the radial part of the wave function. Okay, let me show you another example. See here. Right. Let me show you another example. Okay, I'll take some orbital, not necessarily S alone. We can take some orbital. Say for example, I'll take 4d is a square orbital. Okay, 4d is a square. I'm going to write only the radial part. For angular part, we'll discuss later. Okay. So what's the radial part? Listen, what's the n value? N value is 4. N value is 4. For d subshell, L value is 2. You know very well. 2. Listen, I'm going to write only radial part, so don't worry about this z square and all. Don't worry about that. N equal to 4, L equal to 2. Okay. Listen, but remember, in this orbital I have only z, correct? Z square is there, only z. Whenever only z is present, then ML should be 0. Keep this one, this is very important. Keep this in mind. Okay. If you have only z or z square or z cube, okay, then ML should be 0. Okay. Now listen, how to write the radial part? So first I'll find out n minus L minus 1 value. So n value is 4, L value is minus 2, minus 1. I'm getting n minus L minus 1 is 1. So polynomial should have degree 1. That means it should contain one R value and a constant value. So outright, is it? So radial part of the wave function for this number, that is n value 4, L value 2, okay, which varies with the small r, is given as some normalization constant n, right? n0 into r power. See, now L value is 2, so put r square. L value is 2. Then we should get a polynomial with degree 1. Degree 1 means it consists of a radial 1r term plus a constant term. Okay, this is the polynomial of degree 1 into e power, since it is hydrogen atom Z is 1, so r by n value is 4, so 4 times a. This is the radial part of the wave function for 4d is a square orbital. Write the radial part of the wave function for this orbital 4, px orbital. Yes. Try to write this. So how to write the radial part? Listen, n value is 4. For p orbital, L value is 1. Don't worry about ML. Okay. For radial part, we need only these two orbitals, these two quantum numbers. Now, the radial part for n value 4, L value 1. equal to, it consists of a normalization constant n0 into r power, L value is 1, so r power 1. Then we need to find out L minus 1 value. L value is 4, L value is 1 minus 1, so we get the answer is 2. So we should write polynomial of degree 2. What's the meaning? Degree 2 means we should have AR square term, degree 2, higher power 2. Then BR, then C. We should get a quadratic term, right? Into e power minus, since it is hydrogen atom, Z value is 1, so R by N value is 4, so 4 into A naught. This is the radial part of the wave function, right? Right, now we'll discuss angular part. Angular part of the wave function. Okay, which we represent by the symbol y. Y depends on two variables, theta and phi. Okay, now before going to see how to get the angular part, listen, I'll give you some information, okay, which is very, very useful. First information is, listen, any s orbital, for s orbital, L value 0 and Mn value 0, therefore s orbitals are independent of theta and phi. Independent of theta and phi, which means in s orbital we are not supposed to have theta or phi part. Okay, take them. Okay, s orbitals are independent of theta and phi. This is first point. Listen, this is very important. Remember this. X is equal to r sin theta cos phi. Y is equal to r sin theta sin phi. And z is equal to r cos theta. Okay, remember all these things, very, very important. Okay, now listen. So let me take a simple example. Say for example, I'll take 2pz orbital. 2pz orbital. For 2pz orbital, how to write the angular part? Okay, angular part for 2pz. Okay, which depends on theta and phi is equal to, right? Is equal to. We get some normalization constant. So let me write n1, some value, some normalization constant into. Is it? See here, what is the Cartesian coordinate we have? Okay, since we are writing angular part, don't worry about the r. You know, well, z is equal to r cos theta. Remove the r, just put cos theta. If the angular part contain only cos theta, then the function should be an z function. Okay, the function should be an z function. Okay, this is the one represent pz orbital. Okay. See, 2pz orbital, it depends only on theta, right? 2pz orbital is independent of phi. 2pz orbital is independent of phi. Okay, what does this indicate? Listen, if I plot, see, suppose I take this as this. Say this is plus x-axis, this is plus y-axis, this is minus x, and this is minus y. And above we have plus z, and below we have minus z. Okay. Listen, if you move from plus x to plus y to minus x to minus y, then minus y to plus x. Okay, we are actually changing the phi variable. If we move from plus z to minus z, we are changing the theta variable. Now it is clearly listen, it is very clear from this function that the 2pz orbital function depends only on theta. Okay, now listen, so I'll just focus on theta. If you put theta equal to 0, right, then cos 0 is 1, yes, I'll get a maximum value. Theta 0 means along the plus z axis, right? theta 0. Theta 0 means cos theta is 1. You know very well. Then put theta equal to pi by 2. Pi by 2 means 90 degree. Okay, 90 degree means plus in the xy plane. Right? You put theta equal to 90, cos 90 is 0, so the wave function becomes 0. Then if you put theta equal to pi, that is 180 degree. 180 means the function along minus z axis. Along minus z axis, along plus z it is 0. Then in xy plane it is 90 and minus z means it is 180. Right? So if you plot, listen, the function will go like this. It increases, reaches 0 at 90 degree. Again it increases, reaches 0. Now I have plotted in only one direction. Listen, since it is independent of phi, whatever phi you take, you will get the similar kind of function. You will get a similar kind of function. So you will get an orbital, right, look like a double dumbbell. Okay. Angular node is nothing but nodal plane. Nodal plane. Yes. Listen. In the xy plane, right, if you keep a plane here, the plane passing through the center of the two the upward sphere and downward sphere, between that the plane passing through, where probability is 0, and this plane is called a nodal plane. For pz orbital, isn't the lobes, the upper lobe and the downward lobe are along the z axis. They are along the z axis. Therefore, the nodal plane is present in the xy plane. So for pz orbital, whether it is 2pz, 3pz, 4pz, whatever it is, in general for pz orbital, okay, the nodal plane is the xy plane. XY plane is the nodal plane. And this is what we call as angular node. PZ orbital has one angular node. Okay. Let me take 2px orbital. 2px. Okay, 2px. Listen. In the case of 2px, how the function look like? See, it is x. Therefore, the angular part of the function contain a normalization constant. Let me take the normalization constant as n1 into, for x you will get r sin theta. R, remove that r, so you just put sin theta and cos phi. So to px orbital depends on theta as well as phi. It depends on both. Okay. Now the question is when the function becomes 0. For what theta phi value the function becomes 0. Okay, so what I am going to do, listen, suppose I will take, if you put theta as pi by 2, sin pi by 2 is 1, so I will take theta as pi by 2, theta pi by 2, right? Now, if I put cos phi as pi by 2, phi also pi by 2. Listen, theta pi by 2, phi pi by 2. What is this? Theta pi by 2 means theta pi by 2 means in along plus x axis. I'm sorry. In the xy plane, theta pi by 2 xy plane. Phi pi by 2 means along y axis. Okay.
Sir,
Yeah, I'm sorry. Yeah, I made a mistake. Listen. Actually, the wave function should become 0, right? And what value of theta and phi becomes 0? Listen. What should I do? Let me take theta as 0. If you put theta 0, sin 0.
0, 0.
Sin 0, 0, wave function becomes 0. But if you put cos phi as pi by 2,
1 more. 1 more.
cos 90, cos 0 1 male.
Yes sir. Yes sir. 0.
Yeah. So nana padre pi by 2 instead of pi by 2, I'll take right. We need to find out the nodal plane. So right. Okay, is it? I'll keep things separately. Okay, if I put theta equal to 0 degree, then the function becomes 0. Correct? If I put theta 0, sin 0 is 0, so entire function becomes 0. Or if I put theta equal to pi by 2, sorry, not theta, phi. If I put phi equal to pi by 2, cos pi by 2 is 0, then also the wave function becomes 0. So wave function becomes 0 at theta 0 and phi pi by 2. Theta 0 means along z axis. Along z plus z axis. Okay, plus z axis. Phi pi by 2 means along plus y axis. So this corresponds to plus z axis and this corresponds to plus y axis. So it's called plus yz plane. Yz plane is the nodal plane. And what is the other possible value? If I put theta equal to 180, observe carefully. Theta 180 means sin 180, sin all 180 pi values are 0, right? So then also the wave function becomes 0. Then what about phi? Isn't phi equal to, I'll take 270. Okay, this is 90, 270. If I take phi 270, then also the wave function becomes 0. Isn't theta 180 means that corresponds to minus z axis. Phi 270 corresponds to minus y axis. So this corresponds to yz plane again. Plus yz minus yz. So it corresponds to yz plane. So along yz plane, okay, probability is 0 because the wave function becomes 0. Along yz plane, so yz plane is called the nodal plane. Yz plane is the nodal plane for px orbital. Okay, right. Listen, we can also plot and show, right? For different theta value, you just vary the phi value and you can plot. Okay, that is one idea. You will get the same graph. Okay, but I am not going to do that. Is it? Along x-axis plus x-axis, it's minus x-axis. This is plus z. This is minus z. This is plus y, and this is minus y. You will get a lobe along plus x-axis and another lobe along minus x-axis. And there is a nodal plane, okay, which passes through plus the y and z axis. So yz plane is the nodal plane for px orbital. Okay. A wave function is given. In that wave function, the angular part contains sin theta into cos phi. Then that function corresponds to px orbital. Note down, very very important. If a wave function is given, you can easily find out the wave orbital by seeing which part is angular part is present. Okay. By seeing the angular part, you can easily identify. Now, let me take another orbital, say 3dxy. I am taking d orbital here. Okay. Listen, what is the angular part? Angular part depends on theta and phi is equal to some normalization constant n1 into, see I have x as well as y. X is nothing but sin theta cos phi. What is y? Sin theta?
Sin theta,
right?
sin phi.
This is x and this is y. You multiply these two. So n1 into sin theta
Sin square
theta. And here we have sin phi. Here we have cos phi. Okay. you can combine these two and you can write this as n1 into sine square theta. See, we know very well 2 sine phi, sine 2 phi. Sine 2 phi can be written as 2 into sine phi into cos phi. Sine 2 phi. Sine 2 phi can be written as 2 sine phi cos phi. Bring this 2 to the left hand side. So 1 by 2 into sine 2 phi can be written as sine phi into cos phi. So here I have sine phi into cos phi. So sine phi into cos phi can be written as 1 by 2. 1 by 2 is anyway constant. That constant is included in n1. Don't worry about that. Leave it. So you write this simply sine 2 phi. So if I have a wave function sine square theta and sine 2 phi, then I can say that the wave function should be dxy orbital. Dxy orbital. Okay. For dxy, whether it is 3D or 4D, whatever it is, for dxy, the angular part should contain these two, sine square theta and sine 2 phi. Okay. Now I'll give you some orbital. Say d yz. Okay, 4dyz. How to write the angular part? See, just take it. Listen, I'll write the angular part, which depends on theta phi equal to some normalization constant n1. I have y and z now. What is y?
Sine theta into sine phi.
Sine theta into sine phi. This is y. What is z?
Cos theta.
Cos theta. Correct. Now listen, n1 into, multiply these two, sine theta into cos theta, and keep the sine phi as it, sine phi. Sine theta into cos theta, you can write like this, right?
Sine 2 theta.
Don't worry about this 1 by 2 because 1 by 2 is added in normalization constant. Don't worry about that. Leave it. So, n1 into sine 2 theta into sine phi. This corresponds to dyz orbital. Okay. I'll take say 3d x square minus y square orbitals. Okay. How to get the angular part? Right? How the angular part will look like? See, angular part of this orbital depends on theta and phi function is equal to some normalization constant n1. Okay. This is just a constant, so you can put anyone. N1 into, now I have x square minus y square. What is x? X is sine theta cos phi, correct? Take the square, x square, minus, what is y? Y is sine theta sine phi. Take the square, x square minus y square. Okay, you can write this as n1 into sine square theta into cos square phi. Similarly here, this can be sine square theta into sine square phi. Okay, now I have sine square theta here and here you can take common. Sine square theta, if you take common, you get cos square phi minus sine square phi. Right, what is cos square theta minus sine square theta? Is nothing but cos 2 theta. So, n1 into sine square theta into cos 2 phi. Cos 2 phi. This is the radial part, right, for x square minus y square orbital. Let me take, say, 4d is a square orbital, any orbital. How the angular part look like? Angular part equal to normalization constant into, listen, z square. Actually, what is z square? Z square is not z square actually. Z square is nothing but 2z square minus x square minus y square. Okay. Z square is actually a simplified form. Okay. It's not z square actually. It is actually 2z square minus x square minus y square. Okay. We wrote simply d is a square. Right. But it's not z square actually. It is 2z square minus x square minus y square. This is the orbital. Now, so let me write here. So 2 into, what is z? Z is cos theta. So I have cos square, right? Cos square theta minus x square. X is sin theta cos phi. Square means sin square theta cos square phi. And minus, I have y square here. What is y square? This is y. So y square means sin square theta into sin square phi. Right? Up to this, any doubt? So we have to simplify like this. We take minus sin square theta as common. We get this. This is equal to 1. So if you multiply this by 1, you will get this. Now we can simplify further. N1 into, you take this as 2 cos square theta as such. We can write sin square theta as 1 minus. We can write sin square theta as 1 minus cos square theta. Therefore, this is equal to N1 into, see, here I get minus 1 plus cos square theta. So 2 cos square theta plus cos square theta will give me 3 cos square theta minus 1. This is the angular part for D is a square orbital. Angular part of D is a square orbital. Okay, take note. Is this clear to all? எல்லாருக்கும் இது ஃபாலோ பண்ண முடியுதா? Now I have given a question. You try to find out, okay, the orbital or the quantum numbers. Is it how to find this? Is it those who don't know how to find it, just listen carefully. Is it don't worry about these things and all. See the exponential part. I have e power minus r by some number, right? That number is nothing but principal quantum number. N equal to 3. Then sin theta into cos phi. See, sin theta into cos phi. This is characteristic of x or y or z. Sin theta. Yes.
X, sir.
X. So this is okay. So that corresponds to x. Am I right?
Yes, sir.
Yeah, this is x. So it should be an x orbital, px orbital or py something. Okay. Listen. Listen. You see only theta part. Theta part power is 1, right? Sin theta 1, right? Power 1. Sin theta power 1 means the L value should be 1. Okay, sin theta power 1 means L value should be 1. Okay, don't worry about ML value because ML can be plus 1 or minus 1. ML can be plus or minus 1, anyone. Okay, don't worry about it because we will take linear combination. So don't worry about that. So this corresponds to 3px orbital. This corresponds to 3px. Are you able to follow? So next question, let me give you a question. You try to find it. Si is equal to some normalization constant e power minus r by 5a naught. Okay, into let me give you a function. You try to identify this. Okay, sin theta, cos theta, sin phi. Yes. Yes, n value is 5. Good. Listen, here I have two theta parts, sin theta and cos theta. Sin theta power 1, cos theta power 1. So 1 plus 1, 2. L value is 2. It should be some d orbital. It should be some d orbital. Listen, cos y. So it should be d. So 5 d y z orbital. Is this clear to all? For an hydrogenic orbital, hydrogenic atomic orbital, it is given by some normalization constant r square term e power minus r by 3 into a naught. Then we have 3 cos square theta minus 1. Okay, this corresponds to. Listen, see the e power term r by 3 is there. So that corresponds to n value. N value is 3. And take the cos square term, theta term. Theta power 2 is there, so that corresponds to L equal to 2. So the answer is 3d orbital. It should be 3d orbital, option C. Very simple question. Very, very, very simple. Now I'll give another question. Okay. Take it. Right, this question appeared in 2019 June. This is the wave function given. Some wave function corresponds to some orbital. We need to find out n, L, ml value. Yes. How to do that? Repeat. The question asked here is the unnormalized radial wave function of certain hydrogenic eigenstate is given. Okay, a possible angular part of the eigenstate is. Yes, this is very important. Whenever wave function has common r values, I can take r as common here. Okay, r square, right? Whatever it is, you take In this case, I can take R as common. If I take R as common, then I'll get a constant and R. This is the polynomial. Okay. Now, this R power 1 I get, so it corresponds to N equal to 1. E power minus R by 3, so N equal to 3. So N equal to 3, L equal to 1. Okay, N equal to L equal to 1. That means the possible ML values are plus 1, 0, minus 1. Okay, if it is 0, I'll get cos theta. If it is plus 1 or minus 1, then you should take linear combination. I should get sin theta cos v or sin theta sin v. Those options are not given. So the correct option is theta.